Hello everyone, myself Dr. Bismin Sherif, Assistant Professor, Department of Computer Applications, MES College, Marampally.
Hello everyone, welcome to the second part of the video, Phases of Compiler. Just a quick recap on what we have covered on the part 1 video. So we started with why we need a compiler, then we discussed the formal definition for the compiler, and we discussed some of the phases involved in the compilation process. So for explain the different phases involved in the compilation process, we just took an arbitrary statement position equal to initial plus rate into 60, and we explained what happens to this statement when it passes through the different phases of the compilation process. So the first phase is, we remember the first phase of the compilation process is lexical analyzer. When the statement passes to the first phase, it will generate different kinds of tokens. So a stream of tokens will be generated. These tokens will be given to the next phase of the compilation process, that is parser or syntax analyzer, where the syntax of the program will be checked, and this parse tree will be created as the output of that phase, and this parse tree will be given as input to the next phase semantic analyzer, and semantic analyzer will check whether the meaning or the semantic of the program is correct or not, and it would also take care of different type checking, type mismatch, all those kind of things, right? And now this is given as input to the next phase of the compilation, intermediate code generator, where an intermediate code or an intermediate representation of our search language, or sorry, a source program will be generated. And here the most commonly used intermediate representation is nothing but three address card. Up to here we have explained explained in our previous video, and now we are moving to the next phase of the compilation process, that is code optimization. Code optimization is actually an important phase in the compilation process, because the main agenda or the main target of this phase is to execute code more faster, and also reduce the space that is needed for storing this code, right? So these are the two main target of code optimization. The first one is nothing but execution, faster execution, and second one is nothing but less space. The code should particularly less space to save, to store, right? So this is the main two target of this code optimization. Even though this code optimization is actually an optional phase, um, majority of the compiler works a lot of time on this code optimization, because we know that we are more interested in executing the code much faster, and also usage of low memory space, right? Less memory space. So in this example, in this specific example, we know that temp1 is equal to into real of 60, temp2 is equal to id3 into temp1, temp3 is equal to id2 plus temp2, and id1 is equal to temp3. This will be given as input to this code optimizer, and an optimized code like this will be generated. Let us have a close look on this, what happens to this code, or how this 4-line code is actually get reduced to this 2-line. See, this into real of 60, we know that it's definitely 60.0. We don't need to write it as a function or those kind of things. So we can straightly write it like 60.0. So we don't need this thing, right? We can directly replace this temp1 with 60.0. So temp1 is equal to id3 into 60.0. And now see, here what happens is, at the next step we are adding this id2 with this temp2, and it is getting stored on this temp3, and this temp3 is getting again stored onto this id1. We don't need these kind of repetitions, right? Instead of that, we can directly store this id2 plus this temp1 to this id1 variable, right? So similarly, this 4-line of code can be reduced to this 2-line, which will increase execution speed, and also it will consume only less memory space. So this is the advantage of code optimization. And now this optimized code will be given to the target code generator, or the target code, or the machine code or the assembly code corresponding to our source code or source program will be generated. And for easy to understand, I'm just taking the target code as assembly language. No need to be this is to be in assembly language always. The compiler is capable enough to convert the source code directly to the machine code, right? So here in our example, we are just considering the target code as assembly language, and definitely we need an additional assembler to convert this assembly language code to its equivalent machine sequences. Don't forget that point. And now see here, we are actually multiplying this, here we are using different registers, right? So this R2, R1, all those kind of things, so you can see on this slide actually represent different registers. And the static code generation actually a very tedious process, because we have to have an idea about what are the different available registers, what are the different available memory locations, how the registers can be handled, like how the status of the register can be stored. All those kind of, there's a great stuff of things is actually involved in this target code generator. But here we are I'm gonna giving you a peripheral view only, right? So here we are actually using a register R2, and first of all we need to store this ID 3, that is this temporary variable, to this R2. That's actually what's happened on this first step. Move f id 3 comma R2. So now we have this id 3 on R2, and now we can multiply this R2 into 60.0, and that's actually given us the next statement, malab 60.0 comma R2. Now result is there in R2. Fine. And now again, to perform the second statement, we need to have this ID2 to be in any of the free register, and that's what actually happened in the third statement, move ID2 comma R1. So our ID2 is now available in R1, and thus temp1, that's nothing but the result of the previous operation that's available on this R2. Now our operands are on this R1, register R1 and register R2, so we can perform some addition like addf. So this F actually indicates a floating point operation, no need to worry about that. Addf R2 comma R1, and our result is now this R2 and R1, that's this ID2 and this temp1 will get added, and the result will be stored on this R1. Fine. And now we need to store this result R1 to our variable ID1, and that's actually happened on this last statement, move R1 comma ID1. So this is basically the target code, how the target code will be generated. Each statement in this optimized code will be taken, and its corresponding registers will be identified, its location will be identified, its mnemonic operation, all those kind of things will be specified clearly in the target code. Fine. Again, let me repeat it once again. The target code, there is not any compulsory that the target code must always be in this assembly language. For the ease of explanation, I took it as an assembly language, but majority of the compiler is directly converting the source code to the machine code, to the source, from the source code directly to the machine code, instead of generating this assembly code. The drawback with this assembly code is we have to use an additional assembler to convert this to the target code, right? So this is the different phases of the compilation process. Hope it's clear. And now we have some kind of terms like analysis and synthesis phase. We know that this is the different phases involved in the compilation process. Okay, so this first four phases, that is lexical analyzer, syntax analyzer, semantic analyzer, and intermediate code generator. So all these four phases can be combinedly called as the analysis phase of the compilation process, and the other two phases can be called as the synthesis phase of the compilation process, because the first four phases, that is this analysis phases, actually take care of the analysis of the source program, and this last two phases, it's actually synthesized, so the synthesis the source code to generate the target code. So we have a classification like that also, analysis phase and the synthesis phase. Fine. So this analysis phase can be also called as front end of the compiler, and also the synthesis phase can be also termed as back end of the compiler. And please have an idea about what is this analysis and synthesis phase, and also front end and back end of the compiler. And when coming back to this phases of the compilation, here can see two supporting blocks, right? You can see the symbol table and array handler. So this array handling is nothing but a routine that take care of different errors, which is identified in different phases of the compilation process. The routines or the functionalities, or sorry, or the functions that need to take care of these errors will be there in this is array handling module. And another one is symbol table. You can see in this figure. So whenever the compiler actually meet a new variable, it will be inserted into this symbol table. So symbol table is nothing but a data structure that is capable enough to take care of different symbols or different identifiers that is present in the source program, because it's a mandatory thing, because at the latest step we need to have in certain moments we need in a situation to change the variable value or all those kind of things. So symbol table is it's definitely needed for this compilation process. And that block which you saw on the left side of the faces of the compiler actually take care of the things that's needed to handle the symbol. So that's all about different phases involved in the compilation process. Um, Thank you.